Okay, so let's talk about this from the start. We started talking about central limit theorem. And in central limit theorem, what we discovered, what we examined and discovered, was that there was a relationship between the variability in a population and what samples from that population would look like as well. So in other words, if we had a population that had a mean mu, okay, and we went into that population and we took a sample from that population of size n, well, if we took repeated samples of size n and made a new distribution from it, we would get a new variability for this sample distribution of possible samples from this original population that's equal to the standard deviation of the population, sigma, I'll type it out here since it's easier, divided by the square root of the sample size. Okay, and we call that quantity, we call that standard error. Right, so we start out with the mean and the standard deviation, sigma, of the population, and from that we can derive what the distribution of repeated samples from that population would look like. Well, why is that important to us? That's important to us because we never really know the details of that population. We never really know what mu and what sigma is for that population. So instead, we're stuck with working with a sample that we would take from that population and estimating what mu is. And we estimate it by taking a certain sample size, whatever that might be, and calculating what the average of that sample turns out to be, x bar. Right? That's our mean for our sample. Okay, so let's take a look at an example of this. Okay, so let's say that the population mean is 100, and the population standard deviation is 10. Okay, now if I took repeated samples of size 10, right, from that population, well, how would that be distributed? Well, what we would expect in that case is that x bar is going to approximate the mean for the population, which is 100. So we would expect to get the same mean, roughly the same mean as we get for the population. It's a pretty big sample, not a stretch to imagine that we'd be close to that. But the variability of the sample means because we took sample size is 100. Okay, because the sample size, because of the sample size, we're averaging all the values in that population. So the mean that we get if we took it again and again and again and again, we'd expect it to be pretty close to what the mean is above or below, half the time below, half the time above. Just simply by chance, we'd expect it to be close to that, either above or below that. And the further away from that we get from 100, the population mean, we'd expect to see that less frequently, right? Simply because we wouldn't expect to get an abnormal number of people that are above the mean or below the mean in any particular sample that size. But it will happen occasionally, right? So our sample distribution, if we took our repeated samples over and over again, well, instead of being distributed with a standard deviation of 10, it's now going to be distributed by what we call the standard error, which is the standard deviation of repeated samples of the same size from a population. And what is that going to be equal to? Well, it's going to be equal to sigma, the population of the sample, right, divided by the square root of the sample size. That's shown up behind me? Okay, good. Okay, sorry, square root of sample size. Oh, I should have left that in there with a space. Yeah, that'll stay there now. Okay, so if I calculate that, that's going to be equal to sigma is 10 divided by the square root of the sample size, which is 100, which is 10. So it's 10 over 10. So the standard error is equal to 1. Okay, so now we know that 95, in a normal distribution, we would expect 95% of the distribution of these population or the repeated samples in this case to be between 1.96 standard deviations above the mean and 1.96 standard deviations below the mean. Okay, so we would expect 95% of the time we get a result that's within that range of the mean, and 99% of the time we would expect that would be between 2.58 and minus 2.58 standard deviations, or in this case, in the case of a sample distribution, standard errors of the mean. Okay, so let's take a look at that. What would that mean? That means that if we took any particular sample, if I took a sample of size 100, okay, and I took the average of that, and let's say the average came out to be 99. I took sample X bar, just a single sample, turns out to be 99. If I know the population standard deviation, 10, and I know the sample size is equal to 100, let's say in this case it's equal to 64, and I have a sample size is equal to 64, well then I know the standard error is going to be equal to, it's going to be equal to the standard deviation of 10 divided by the square root of the sample size, which is 64, which would be 8. So our standard error in that case is going to, oops, that was tricky, equals 10 divided by 8. Hopefully it won't do that to me again. Okay, it's formatting issue. Let me just format this as numbers. Okay, there we go. Standard error is going to be equal to 8 divided by 10. Up to 10 divided by 8, excuse me. Okay, it's going to be equal to 1.25. Well, we know because of the nature of a standard normal distribution that we would predict that the true population mean is going to be between, if I want 95% confidence, is going to be between 1.9 standard deviations below and above what I calculated my mean for my sample is going to be. So that would mean that my sample, my confidence interval, which is going to be equal to X bar plus or minus, right, 1.96 times the standard error, which in this case is 1.25. That I would expect X bar, if I start with X bar with 99 in this case, that I would expect, but that the true population mean 95% of the time is going to be between these two values, minus 1.25 times 1.96 and plus 1.96 times 1.25. Or in other words, if I calculate it down here, it's going to be equal to 99 minus, I'm going to call this 2 for our purposes, 2.5, and 99 plus 2.5. Okay, I'm just doing that to make it a little bit quicker. You should actually calculate it. Okay, oops. So we're 95% confidence that the true population mean is between 96.5 and 101.5. As it happens, this time we're in luck. We got it right. It is the true population mean is 100. So in this calculation, we actually did capture the true population mean between these two numbers. So if I asked you, if I did this 20 times, how many times would you expect to capture the population mean? If you repeated this, took a new sample, got a new mean, how many times out of 20 would you expect to capture the true population mean between these two values? Okay, you guys online too. I need some input from you guys online. Exactly, 19. How about if you did it 100 times? If you did it 100 times, you'd expect 95 times out of 100. That means that 5 times out of 100 or 1 time out of 20, you're going to be wrong. You're going to say that I'm 95% confident that the true population mean is between these two numbers, and 1 time out of 20, you may be incorrect that you didn't capture the population. Might be a little lower or a little bit higher. Probably not far off, but just a little bit further off. Okay, so now one of the problems that we have is that in addition to not knowing what the population mean is, we generally don't know what the population standard deviation is either. So I really can't just use sigma here and divide by the square root of n. I'm really stuck, instead of using sigma, using the standard deviation from the population as I just calculated it. So let's see, what would that mean? That would mean now that I'm going to do another example. X bar, right, is let's say it comes up to be 98, and my standard deviation of my sample is equal to, let's see, standard deviation of population is 10. This should mimic that, at least come close to it anyway. I'm going to say in our particular sample, it turns out to be 12. Okay, so now if I want to calculate what my standard error for my repeated samples is going to be equal to, it's going to be equal to the standard error is going to be equal to, let me put a space in there, it's going to be equal to the standard sigma. Well, wait, I don't know what sigma is, right? So I have to use the standard deviation instead of sigma divided by the square root of the sample size. Okay, well now when I calculate that, what's that going to be equal? I'll say it's the same sample size as before. What did I say? 64 before. Okay, I'll keep it the same. So my standard error now is going to be equal to the standard deviation divided by the square root of the sample size. Oops. Is equal to the standard deviation divided by the square root of the sample size, which is 8. Okay, and that's equal to 1.5 this time around. Okay, so now when I do my 95% confidence interval, okay, I'm going to change this one little bit. I'm going to make this, instead of a sample size of 64, I'm going to make this a sample size of 25. So now when I calculate my standard error, it's equal to my standard deviation of my population, because I don't know that the population is 10, so I got to use my standard deviation of my sample, divided by the square root of the sample size, which is 5. Okay, so my standard error now becomes 2.4. So now, once again, I want to calculate my confidence interval. So now I'm going to say my confidence interval is equal to, well, what's it going to be equal to? It's going to be equal to, okay, it's going to be equal to X bar, just like before, plus or minus my standard error times, a z-score, 1.96, times my standard error, which in this case is 2.4. Well, there's a problem here. Is it? Anyone would tell me what the problem is here with this formula? By using the standard deviation instead of sigma, I've introduced an extra element of possible error, of uncertainty, right? Because we start off with this formula assuming we know it. Yes, very good, Jennifer. And starting off with this, we know what it is. By using the standard deviation of the sample instead of the population standard deviation, we've introduced that extra element of uncertainty. So now we have to use the t-value for 95% instead of using the z-score, 1.96 for 95%. So instead of 1.96, I now have to substitute a different number in there. Okay, let's see. So how do I find out what I need to put in there? I have to look at my t-score on my tables, right? So I'm going to look up the one I usually use. See if I can't find it quickly. Let's see. Here we call it table. Okay, you're ahead of me already, right? Okay, let me pull it up here so we can all see it together. I think you're right though. Okay, and it disappeared. Let me try that again. Here we go. Okay, so here it is. Both of them popped up that time. So here it is. So my 95% confidence interval requires that I use this t-value in this column. So if I scroll down here, notice that instead of using the sample size, we're using the degrees of freedom, which in this case for confidence intervals equal to sample size minus 1, or 24 in our case. So 24 is going to be 2.064. So instead of using 1.96, I use 2.064. So what does that do? That makes the confidence interval wider, which makes up for the increased uncertainty. Since it's wider, I make up for that increased level of uncertainty by not having the knowledge of what sigma is. Okay, the wider the confidence interval is, the more certain I am that I'm going to capture that a true population mean in between those two. So in this case, it's going to be equal to 98 plus and minus, plus or minus, minus, and I'm going to call that about 4. I'm going to call that roughly 4.9 for our purposes. So it's going to be equal to, whoops, 98 plus or minus 2.2. I'm going to call it 4.9. 4.9. Yep. Okay. I'm put a space in front of there so it doesn't calculate it. 98 plus 4.9 and 98 minus 4.9. Oops. Okay, so between 93 and 102. Wider interval than we got here, than we got before when we could use 1.96. Also, it was a bigger sample size here as well. Let's take a look at the impact of the sample size. Okay, first of all, number one, what is this portion of this that we're adding and subtracting from our sample mean? What's that part called? Anybody recall what the name is for that is? We know that the standard deviation of the repeated sample is called the standard error. But what is this part? The part where you multiply the z or the t-score times the standard error and add or subtract it. Recall what we referred to that as? Well, normal life. What would you, if I told you it's between 9 and 7, it's +2 or -2 on this price or something like that, or this weight, if I guessed your weight and I'd say plus or minus 10 pounds, margin of error, right? Perfectly good name for it is a margin of error. In other words, this portion of this calculation is called the margin of error, the amount that we're adding and subtracting. Yeah, I got a couple of people online got it. Margin of error. Let's see what the impact of the margin of error is on the confidence interval. Okay, or at least on the standard error, because that's what we're the margin of error which we're multiplying. We're getting by multiplying the standard error times the t-score. Okay, so let's see what that's going to mean. Okay, so it's equal to the standard deviation divided by the square root of the sample size. Okay, so now I'm going to make up an example of this. Okay, there's our standard error. Okay, whatever t is or z is, we're going to be multiplying that by this. Okay, how does the sample size affect the standard error? Okay, well, let's say I gave you an example, said that the standard deviation was equal to, and I'll move this up a little bit. Standard deviation is equal to, let's say 10. Okay, so let's say that the sample size in this case, the sample size is equal to, let's say I'll start off with the sample size is equal to, let's say sample size is equal to 9. Okay, so now what is my standard error going to be equal to? It's going to be equal to 10 divided by the square root of 9, which is 3. Okay, 3.33. Well, let me see what happens if I double my sample size, make it 18. It's going to be kind of a sloppy number here, isn't it? Okay, let's see what happens here, though. It's going to be equal to 10 divided by the square root of 18. Well, gee, it got bigger. It got smaller, right? It got smaller because the sample size is on the bottom of this fraction. If it had been on the top, it would have gotten bigger if I got a bigger number. Since the square root of n is it becomes a bigger number, the standard error becomes smaller. Let me double this again. This time equals 36. N equals 36. See what happens now. Equals, let's see, is equal to 10 divided by, well, let's see, what is the square root of 36? It's 6, coming out to 1.666. What's the relationship between 3.33 and 1.66? Let me just take a look at this. It's half. So what happened here? I doubled the sample size. What happened to the size of the standard error? It was halved, right? So gee, what does that tell you? That tells you that since you double the sample size, I halved it. Yeah, I quadrupled the sample size, it halved it. Well, why did that happen? Well, because you're taking the square root of the sample size, right? So in order to get a narrower standard error, if you want half the standard error with the half of the standard error, so you get a narrower confidence interval, you need to quadruple the sample size. What happens if I multiply sample size by 9? 9 times 9 is 81. What does that do? Okay, well, let me think about that. If I multiply it by 9, it's 9 times bigger, but it's on the bottom, you're taking the square root. I'm going to predict it's going to be divided by 3. It's going to be 1/3 of what the standard error was before. Let's see if that works. Equals 10 divided by square root of 81 is 9. Is equal to 1.1. It's 1/3 of that sample size. Okay, that's the relationship between these. And you can see the impact of sample size has on confidence interval. As the sample size gets bigger, the confidence interval gets smaller, right? So that gives you one way to get a tighter confidence interval is to use a bigger sample. Also, to be more reliably able to reject the null hypothesis with T, as we're going to see later on, it works the same way. The bigger the sample size, the more reliable is your result, and the narrower your confidence interval. Okay, so the only twist on this that, of course, we run into very frequently is that we'll be working with proportions sometimes instead of with means, for instance. So if we're looking at a proportion, if I told you that we surveyed people in New York City and we took a survey of 1,000 people, and out of those 1,000 people, 450 were planned on voting in the next election. And I asked you, what is the proportion of people in our sample said they're going to vote in the next election? Our proportion is 450 over 1,000. In other words, 45% of the people we surveyed said they're going to vote in the next election. But if I took another sample of 1,000, I might get it 43%. Another sample, I might get 47%. Another sample, I might get 44. Another one, I might get 45 again. Who knows, right? So what this tells us is that we might have a normal distribution around this of samples that we can build around this proportion that we got from our sample. And it works exactly the same way. Proportion that we calculated, p cap in other words, which we got from our sample, plus or minus, right? Plus or minus 1.96 for a 95% confidence interval times the standard error. Okay, when we're working with proportions, we're generally working with very large sample sizes. So typically, you won't be worrying about the t-score with them. You just be worrying about whether you want a 95% confidence interval, 1.96, 99% confidence interval, 2.58, and so on. So I'm going to stick with our z-score of 1.96. But now, how do I calculate the standard error for repeated samples from a population for a proportion like this? Okay, well, standard error for a proportion is going to be equal to, and we have that document that is in that particular class that outlines how to do all of these. Is going to be equal to, standard error is going to be equal to p, the square root of, and all this goes together, p times 1 minus p, the proportion times 1 minus proportion over n. In other words, the square root of this whole thing is going to be underneath our interval right here. All of that square root of p times p over 1 minus. So what is that going to be equal to? It's going to be equal to, I'm going to do this in steps. P times 1 minus p is equal to 0.45 times 0.55, 1 minus p, divided by the sample size, which is 1,000. Okay, and all of that, since it's all dividing and multiplying, we can go ahead and hit enter. I don't need parentheses, presumably, and that's the answer that I get. So now, if I take this, I want to find the square root of it. right? Because I want the square root of p times 1 minus p over n. So square root of this whole thing is equal to 0.0157. I'll call it 0.016. Okay, so now how do I calculate my confidence interval for this proportion? Well, again, it's equal to p cap. And what was p cap equal to? Equal to 0.45, right? Plus or minus 1.96 times my standard error, which is equal to 0.01. I'm going to call it 0.016 to make this a little easier. Okay, 0.016, about 1.5%, a little bit more than 1.5%. Okay, so 1.96 times this, I'm going to round that off to 0.32. So I'm going to say it's equal to 0.45 minus 0.032 and 0.45 plus 0.032. So despite all my rounding, you can see that this is going to be my confidence interval right now. I have a sample, 450 out of 1,000 people said they were planning on voting this year. My proportion for that sample is 45%. The true proportion, my 95% confidence interval, the true proportion of the entire voting population, what proportion of them would say that they were voting this year, is between 0.418 and 0.482. And of course, like many of these analyses you can do, a couple of presumptions is that these samples are random and independent, right? So we want to make sure that study design is correct. Okay, so that's the way we would work with confidence intervals. So now what about hypothesis testing? How do we apply this now to compare the means of a sample to a fixed value, two samples from two different populations to see if the means are the same or different? So I'm going to move over to SPSS to do that. Okay, and I'm going to try and pull up a, let me get this out of the way. Can you show me how you got the standard error again? I'm tell you what, because our time is so limited, if I get time to go back to it again, but remember that we've recorded this. So the question there would be the standard error for what? Standard error for proportion or the standard error for a sample mean, right? So proportion. Okay, actually, let me pull that back up so I can show you real quickly in that case. So I probably won't get back to that again. Okay, the standard error is equal to, for proportion, standard error for proportion is equal to the square root of p times 1 minus p divided by n. Okay, so imagine all of this. I don't have my graphics tablet, maybe so I can't draw this. Well, maybe I can try and draw it anyway. Give that a try. That would be the square root of p times 1 minus p, right? This in parentheses, right? Because I do the subtraction first over the sample size, right? In this case, that would be 0.45 times 0.55 over n, which was, in this case, n was 1,000, right? So once I resolved this, this turned out to be 0.000247. I'm not going to bother to write that out, right? 0.00275, something like that, right? And then I still have to take the square root of it because square root of this whole thing. So I take the square root of this whole thing. I mean, since it's a fraction, the square root of it actually comes out to be a bigger number, not a smaller number. And it comes out to be roughly 0.016. It was really 0.0157 something, but roughly 0.016. How did I get the point? 1 minus p. The p is 0.45. 1 minus p is 1 minus 0.45. Okie doke. Okay, good. You got that clear, I hope. Okay, good. So let me move on to the t-test, and let's talk about hypothesis testing, and let's talk about Let me open one up and see one data set up. Let me see session. I think session 8. Oh, session 8 is probably analysis of variance. Let me see what's in here. Now, of course, all these calculations are going to be quicker in SPSS than they are in Excel. Okay, here is this is a data set which has the forced expiratory volume, the liters of air that someone can expel in 1 second, okay, from their lungs. And we can see there's a lot of variability in here and so on and so forth. And all I have for, say, 60 workers, my sample size is 60, I have a numerical variable which tells me what each person's score was on this pulmonary function test, this FEV1. Okay, so one of the things I can do from this is I can say, let's say that these are all workers in the steel industry that are between 40 and 60 years old. And I wanted to know what's the average FEV1 for all steel workers between these ages. If I can't afford to go out and sample all test all steel workers, one of my options is to take a sample of, as in this case, 60 randomly selected steel workers and work with the sample instead. So I'm going to say analyze, because I want to find out now what my 95% confidence interval is going to be. I'm going to say analyze, and I'm going to say descriptive statistics, and I'm going to start with descriptives. Okay, and I'm going to take pulmonary function FEV1, move it into my variables box, and in options, I'm going to tell it I want the standard deviation and the mean. I want those for sure. I want the standard error of the mean also. So I'm going to click continue, and I'm going to say okay. Okay, what do I wind up with? I wind up with the mean expiratory volume is 2.83 liters in that first second. And my standard deviation is equal to 0.52178. Okay, so that's my standard deviation. This is my standard error. Any remember, how do I get from my standard deviation to my standard error? Right, my standard error is equal to the standard deviation divided by square root of the sample size, right? Right, square root of n. Okay, right. It's not n, but square root of n, right? Okay, so if I take 60, what's the square root of 60? Let's see. Let me get a calculator up here. Okay, so let's see. Clear. So 60. Whoops. My sample size is 60. I'm going to take the square root of our sample size is equal to 7.34. I'm going to put it into memory so I can get to it easily. And I'm going to clear it. And then I'm going to say, okay, my standard error is 0.5218, I'll call that. And I'm going to divide it by my square root of my sample size, which is equal to this. Oh, I messed that up. I must have hit it twice. Let me do that again. Okay, 60. It's square root, memory plus, clear, and let's see, 0.52178 divided by, and recall square root of my sample size, and it comes out to be 0.067. Well, here it is. Standard error is equal to 0.067. Exactly. SPSS calculates it exactly the same way we do it. Now, what will my 95% confidence interval be? Right? Well, my 95% confidence interval is going to be the mean plus or minus some value, 1.96 for instance, times 0.067. Well, you want to know something? If I actually did that, I'll do that in Excel so I can go back to it again. Let me see if that actually works. Let me get some fresh space here and move this up. See if that actually works. So what did I say that was? It's 2.83133, right? And then my standard, my margin of error is going to be equal to 1.96 times my standard error, which is 0.067362. I'm trying to do this as precisely as possible. So plus or minus that number, that margin of error is going to be equal to this minus my margin of error, or this plus my margin of error. Okay, now I'm going to get SPSS to do this calculation for me. Is this the numbers that it's going to wind up? What do you think? Is this what I'm going to get for my answer for my 95% confidence interval? Oh, you know, I just did something wrong there. Equals this plus. I'm not sure why this didn't work out, but that's better. Okay, is that what I'm going to get? I think not. I think it's not going to be quite exactly the same thing. Okay, let's do it. Analyze, descriptive statistics, explore, because explore now will give us the margin of error. I'm going to pulmonary function test in there. I'm going to ask us to do all of those, including the 95% confidence interval. I'll click OK. Let's see how SPSS calculates it. Okay, let's see. The mean is, just as we said before, 2.831. The standard error is 0.067362, just as we got before. Let's see what our 95% confidence interval is. It's 0.2696. Wait a second, it's just a tiny bit different. And that end is tiny bit different also. Anybody want to hazard a guess as to why that's different? The sample size is 60. Since I don't know the population mean, what should I have used instead of 1.96? I should have used a t-score for 59 degrees of freedom, right? So it's very close, isn't it? Right? It's really very close, but it's not exactly the same because we should have really used the t-score. And the t-score in this case would have been, let's see if I don't have it open anymore right now. Oh, that's a good question. Well, how do you know whether or not to use the t-score? On a practical basis, when the sample size gets very large, let me pull up the t-table again. Okay, if I pull up the t-table again, okay, as the sample size gets very large, look what happens to the value of t. Gets closer and closer to what value? 1.96. Matter of fact, the sample size of 100, it's 1.98 instead of 1.96. But a small sample size, it's quite a bit different, isn't it? Makes a big difference. Big sample size makes less and less difference. On a practical basis, if you have a large sample size, like over 100, it's likely you would ignore that t and just use 1.96, only because it's just so close, right? But SPSS doesn't take that shortcut. Doesn't matter what the sample size is, even if the sample size is 5,000, SPSS is going to use its calculated value for the t value instead of using 1.96. Like for 1,000, let's say that the t-score, the z-score would be 1.96, but the t-value for that sample size might be 1.96001 or something like that. It'll still use that to calculate it, only because it can. It's just as easy for it to use the t-score as use the shortcut of using 1.96. Okay, you guys okay with that? So you saw what I just did there to get the confidence interval using SPSS. Okay, so now I'm going to do another test now using the confidence using SPSS again and the same data set. This time I'm going to say compare means. Okay, now how many samples do I have here? How many population samples do I have here for FEV? I only have one. I only have those steel workers. I don't have steel workers in Pittsburgh versus steel workers in the Ruhr Valley in Germany or something like that, right? So I only have one sample. So this is going to be a single sample t-test. Okay, so how would this work? Well, what I would do is take my pulmonary function test for my 60 workers that I've sampled, move it into the test variables, and then I would say, what do I want to compare it to? Well, in a single sample t-test, you're comparing it to a set value. So for instance, maybe that said value is that the workers in the Ruhr Valley have lung FEVs that are equal to 3.0, right? Maybe they're big guys, they got a lot of lung capacity, they're 3.0. Now my mean was 2.83 for these 60 workers. But that we don't know if that's really truly the population mean for all workers in the United States, all steel workers in the United States. So we need to test whether we have enough information to say with 95% certainty that our workers, our sample workers, represent a population mean that's the same or different than 3.0, the known population mean for workers in the Ruhr Valley, where we tested everybody, right? Where Germany, they have universal health care and they tested everybody, right? So how can we compare these two? That's going to be our hypothesis test. So with a single sample t-test, we're testing it against a certain value. So for instance, our null hypothesis might be the mean mu for workers in the United States is equal to mu for workers in Germany, except we know the value for the mean for the population in Germany is 3.0. So instead of saying mu for workers in the United States equals mu for workers in Germany, we could just say mu for workers in the United States is equal to 3.0 is our null hypothesis. And our alternative hypothesis might be mu is not equal to 3.0. Will the test value be given? I'm not sure. Yeah, will it be given, but it might not be. It might not be like it might not smack you in the face. It may be buried in the words in the example, right? Like just now I mentioned, oh, all the workers. We know the mean for all the workers in the Ruhr Valley is 3.0, and their this age range, and their blood pressure is this, and their whatever. So it might be in there. You have to parse it out, right? Or it might just tell you that you're comparing it to that value. Okay, but usually it's pretty easy to identify, right? Because it's going to be an actual value where where the other part of this is going to be a sample of from a population. This is a sample from a population. This is a known mean for a population or a known value we want to compare it to. And options at this point here, I can tell that I want a 99% certainty. In other words, alpha is equal to 0, 1, or more commonly 95% confidence. In other words, alpha is equal to 0.05. So I'm going to click OK, and it will do our test. The t-score comes out to be minus 2.504. In other words, that's the number of t-scores apart that these two values are, with 59 degrees of freedom. I happen to remember that the t-score for 95% confidence for this number of degrees of freedom was 2.03 something. 2.03 something, and this is larger than that is, right? We don't worry about the sign. This is larger than that is. So the t-score is large enough, bigger than our critical value of t, that 95% confidence value for t. So we can reject that null hypothesis, but we really don't even have to rely on that, because SPSS tells us that associated with this t-score and this degrees of freedom, the probability we'd be wrong if we reject the null hypothesis is under the significance, two-tailed significance, 0.015, is 1.5%. Since this probability of being wrong if we reject the null hypothesis is less than 1%, we say to ourselves, we can reject the null hypothesis and accept the alternative hypothesis. Okay, that's typical of a single sample t-test. Okay, now, what are the other options here? The other options is two sample t-tests, right? Or a paired sample t-test. Okay, so let me go up here to analyze and you'll see those. Compare means, one sample t-test, independent, in other words, two sample t-tests, and paired sample t-test. Okay, let's go into independent samples t-test, except that we need something to compare it to. So I can't use this data, I can't use that data file. I need another data file. Okay, so let me see if I can't quickly find one. Let me see if I can find session 7. 7 or 8. Session 7. Yeah. Yeah, here you go. This is a good one. Okay, two sample t-test. I'm going to open up this data file. And in this situation, we have two samples. Start it up SPSS again. Okay. Oh, I lost it. Okay, let's see. Let me see where this is located. Let me bring this to the top here so I can get to it. Okay, open, data. I'll navigate to my desktop and I'll go to, oops, it's not the one I want. I want session 7. So I'll go back to my go back to my desktop and session 7 and two sample t-test. Okay, here's our two sample t-tests. In this case, we have two groups. Under gender, we have male and female. We have two groups, and we have scores for each of those two groups. In other words, if this were an Excel file, we might see male and female here, and the female scores here, and the male scores here. But in the way SPSS arranges this, it identifies the uh, uh, categorical variable in one column and the numerical variable in the other. So let's compare the means of these two groups. Analyze descriptive statistics. In order to separate this out into the two groups, I have to go into descriptive statistics, explore. I can't do that in descriptives because descriptives will only count these numbers all from the same population, not as males and females. So I'm going to go to explore instead. And in explore, I'm going to say the values of scores go into the dependence list, and the gender, the categorical value, goes into the factor list. And then I say to myself, okay, let's go ahead and calculate these statistics. I'm going to calculate all of the statistics, 95% calculation, for these two values for gender. So what does it do? It calculates the score for females is 10. The score for males is 7.56. Now the question becomes, are these two values different enough that I can start with the null hypothesis that the mean for the entire population of males, not just this small sample, the entire population of males is equal to the mean for the entire population of females, right? That's my null hypothesis. My alternative hypothesis would be is the mean for females is not equal to the mean for males. Okay, so let's take a look at this. Let's see, it's 10 and the 7.56 are the two means. It does seem like there is some difference there. Let's take a look at this. Analyze. Now I'm going to compare means. This time it's an independent samples t-test. Two different samples. Okay, test variable is going to be the value, the score. And then the grouping variable is going to be break it up into two groups, male and female. Now I don't recall. I believe that male and female was identified as a 1 and a 2. If it doesn't work, I'll have to go back there and do it again. Tell it that 1 is female, 2 is male, and click continue. See if it works. Okay, it looks like it worked. Okay, so I get, here it repeats our statistics for descriptive statistics. The female mean is 10. The male mean is 7.56. These are samples though, and they're small samples, and we're comparing the two of them. So we perform a two sample t-test. We compare the mean x bar 1 minus x bar 2 divided by the standard error. Now you may remember when we calculated standard error for independent samples t-test, we used two different formulas for the standard error. One we used when the samples had equal variances, or we assumed equal variances, and the other when the samples had different variances. And our rough rule was if the standard deviation of one group is double that of the other, we said reject the idea of equal variances and we assumed unequal variances and used that formula for standard error. Since these, one is not double the other, we probably would have assumed, let's say that the standard deviations are roughly this equal. We'll assume them to be equal. SPSS actually does a test for that. Levene's test for equality of variances. So this first section here is testing for the equality of variances. And SPSS actually does the t-test, which starts here and goes to the right. This is the start of the t-test here. It does the t-test twice. Once, assuming equal variances, like we would have assumed from our guess up here, and the second time for equal variances not assumed. It actually does the test twice. Okay, so up here we would have assumed, let's do it equal variances assumed, right? Well, SPSS actually does a test for that. It assumes equal variances to start off with, just like any null hypothesis, and says that if the probability of being wrong, if we reject that, is less than 5%, I'm going to reject that and use the bottom line instead. Equal variances not assumed. Is that test, does that have a probability of less than 5%? No, it doesn't. So that means I can't reject this null hypothesis. Equal variance is assumed, so I'm going to stick with the upper line, just as I would have assumed up here, since that one was not double the other for our kind of quick and dirty kind of guess at that. Okay, but so we stick to the top line. And the t-score is 2.184, and the degrees of freedom is 16. And the probability we would be wrong if we reject the null hypothesis, mu, the mean for males is equal to mean for females, probability we would be wrong is 0.044, 4.4%. Okay, in other words, less than 5%, less than 0.05. So we reject the null hypothesis and we accept the alternative hypothesis. Okay, so that's the way that we would deal with this. Sometimes you're going to be using the bottom line. Sometimes you're going to be using the upper line. Okay, I think in the test I didn't ask you, actually, I may have asked you to do an example in SPSS and feedback the answer. So there were a couple of other choices there, weren't there, though? Okay, what were those other choices? Let's take a look. Okay, let me get this out of the way for a second. Let's take another look at the other choices here. Compare means. We also have something else we looked at, which paired sample t-test and analysis of variance. Okay, so let's take a closer look. Now, let's take a look at paired sample t-test. Let me see if I can't find that. An example of paired sample t-test. I think I got one in there. Open, data, session 7, paired sample t-test. Okay, I'm going to open that and take a look at what's in there. And we have a numerical variable and a categorical variable, except it looks a little bit different this time. Placebo and drug are lined up in columns next to each other. That's unusual for SPSS, isn't it? Normally, you'd expect to say a drug in one column and the performance of the drug, whatever these values represent, say pain levels or something like that, in the other column, right? So this is quite different. What we're doing here is, yes, we're doing paired sampling. What we're doing here, I don't recall off the top of my head if there's a problem on the exam on paired sampling. So it could be kind of just a question or something like that. But what's happened here is we have 9 subjects here. Subject number 3 took the placebo and his pain level was 8. And he took the drug and his pain level was 4. Oh, it went down. Okay. Subject number 2 took the placebo and his pain level, maybe he took it for 2 weeks. Pain level reported was 7. He took the drug for 2 weeks and his pain level was 5. Now, notice that these don't always happen in the same direction. In other words, randomly, some of these might have taken the drug first and then the placebo. But the point here is that these are results for the same conditions, for the same 2 different conditions for the same person, right? So what we can do is we can actually just measure the difference. Now, that this person, the difference was 0. This person, the difference was -2. This person, -4. This person, +3. This person, -2. We can now just take the differences and see if there is a difference among all of these people, if the average difference among all of these people is a significant player here, if it looks like that drug is working better than the placebo. Well, what's our null hypothesis here when we compare two paired samples? Our null hypothesis is that there is no difference between taking the placebo and the drug. So if I take the average of all the differences, I would expect the average of all the differences to be zero. Sometimes higher, sometimes lower, but average zero over the entire 9 people, which represent a sample. Okay, well, what would be our null hypothesis then? Well, our null hypothesis is that the difference between the placebo and the drug, the difference is equal to zero. And our alternative hypothesis is that the difference is not equal to zero. So a paired sample t-test is really just a certain kind of single sample t-test, except the value that we're comparing the differences to is zero. That comparison value is zero. Okay, so we want to know if the differences are statistically significant, then zero. So I'm going to go ahead and do this analysis. Analyze descriptive statistics, compare means, paired samples t-test. I'm going to move, notice that it won't let me do this. This won't light up until I move two variables in here. The value for the placebo and the value for the same people for the drug. Okay, for the same person for the drug. Okay, options. I have my chance to tell if I want a 5% alpha or a 99% for a 1% alpha. So I'm going to leave it 95%. I'm going to click OK. SPSS will do our calculation. And notice it really does basically a t-test, right? So the paired sample t-test, the mean is 1.596. That mean is being compared to, the mean is equal to 1.596. In other words, the difference between the placebo minus the drug averages, all those differences averages 1.556. The standard deviation and standard error for those values, -1, +2, -1, 0, minus, and so on and so forth. Standard deviation, 0.89, and the standard error is 0.89, and the standard deviation is 2.698. Okay, so now SPSS calculates a t-score for the difference between 1.556 and the value 0. And that t-score is equal to 1.73. And the p-value, the probability you would be wrong if you reject the null hypothesis. What was the null hypothesis again? The difference is equal to 0, right? Was the null hypothesis. The alternative hypothesis was the difference was not equal to 0. So would we be wrong if we reject the null hypothesis here? Right, exactly. We failed to reject the null hypothesis in this case. Another way that we can confirm that is by looking at the 95% confidence interval for the true mean. And the true mean, right? If the true mean can possibly be, with 95% confidence, can possibly be 0, then we fail to reject the null hypothesis also. And since our confidence interval for the true mean, if this were everybody taking the whole population taking this drug, the true mean would be for 90. We're 95% certain the true mean for the differences between minus 0.5 and plus 3.6. So 0 is between those two. So we can't say that it's different, that the true mean for the population is different than 0 with 95% certainty. Because in order to say that, we'd have to have it outside of the night. 0 would have to be outside of this confidence interval. So almost, virtually always, you'll see that the 95% confidence interval and your statistical significance for your t-test will agree with one another. Okay, so last but not least, what happens when we have more than two groups, more than two populations we want to compare the mean of? Well, now we have a real issue, don't we? And the problem there is that, let me see if I can't find one. I think that's only got chi-square in here. Yeah, I don't think that's going to work first there. I need session. Wait a second, let me go back to session 8. Maybe I got something in here. Okay. Not going to need session 9. I think this might do for us. Let's see what I have here. Okay, I'm going to open up another data file. Open data. And I'm going to go back to my desktop and go into session 9. So let's see if I got something. Let's see what this has got in it. Okay, so now here, let's take a look at, let's take a look at, I'm not sure what these numbers represent. Let's say they represent pulmonary function. Oh, how about they represent for the percent? Let's say these numbers represent the percentage of people who smoke in different states for different income levels, right? So, or different age ranges, right? So age range 1 might be youngest group, age range 2 might be middle age group, age range 3 might be the oldest group. So we have, I'm going to show the values here. The numbers are actually there. We have 3 groups in the age group. We have 3 values in the age group: young, middle age, and older. And we want to compare the mean for the younger percentages for the younger smokers versus the middle-aged smokers versus the older smokers. So what would be our null hypothesis there? Our null hypothesis is that the mean proportion of smokers by state in the youngest group equals the mean in the middle-aged group equals the mean in the oldest group. And our alternative hypothesis would be, well, hang on a second. If this were a t-test, we might just say mu1 does not equal mu2, or mu2 does not equal mu3. Well, the problem with that is in order to show that, we would have to do the t-test numerous times and break it up into into two groups each time. For these 3 groups, we would have to do 1 versus 2, 2 versus 3, 1 versus 3. We'd have to do it at least 3 times. Now, for this group with 5, we would have to do it 1 versus 2, 3, 4, 5, 2 versus 3, 4, 5, 3 versus, and so on and so forth. We'd have to do it more times, right? 20 times or something like that, right? So repeatedly doing the t-test opens you up to a more and more likely chance of error. So we need a tool that will allow us to compare the means of, say, 3 groups or 5 groups at the same time. And that's where analysis of variance comes in. Okay, let me just take a quick look at the questions here. Please reiterate how to determine the factor list versus the group list. Okay, and SPSS. Okay, so we're about to do that now. So I'm going to say analyze. So now I'm going to go into compare means, because that's really what I'm doing here. Even though it's called analysis of variance, I'm really comparing the means. Compare means, one-way analysis of variance. And now I have 2 groups. I have 2 choices here. The dependence list, this is always going to be my numerical variable, the thing I'm going to find the mean of. What's the mean? It's going to be the mean. This is my numerical variable here, that little ruler. It's going to be the mean percentages for different states. And what are my factors? My factor is the groups I'm breaking it into. In this case, I'm going to start out with age. So I'm breaking it up into 3 ranges of age. So I'm going to look for averages for younger smokers, older, middle-aged smokers, and older smokers. Okay, so I'm going to click OK. Analysis of variance is going to test those means, and it's going to determine that the probability that all 3 of these means are the same is very, very small, based on the sample size, the variability within the groups, and difference between the averages. The probability that mu1 is equal to mu2 is equal to mu3, mu for younger, equal to mu for middle age, equal to mu for older, is very, very small. It's less than 1/10 of 1%. So that means I can reject my null hypothesis, mu1 equals mu2 equals mu3. But this does not mean that mu1 does not equal mu2 does not equal mu3. Or it does not mean that there's no association, or it doesn't mean that there is an association between all of these. What it means is only that at least 2 of the means are different from one another. Okay, that's it. Not anything about all of them or implications about relationship for all of them, only that two of the means are different. Good. Do we ever hypothesize that mean could be greater? Yes. That is called a one-sided t-test, a one-sided test. Okay, and you want to know something? I'm going to stay away from that for now, and I'm going to bring that up as we get to the end of the semester. I am going to introduce that at the end of the semester. I probably won't put it on the third exam. I'm going to bring it up before the end of the semester. The difference between what we do, which is a two-sided t-test, which you see in SPSS, that's two-sided, right, over the significant, which is a two-sided t-test. A one-sided t-test is kind of a cheat in some ways for a couple of reasons. One is that you already, before you do a one-sided t-test, you have to make assumptions about what you think the outcome is going to be, number one, in order to build that hypothesis. And number two, it's less rigorous test. Then it's easy to reject the null hypothesis. So one of the reasons for using a two-sided t-test, even if you were considering a one-sided t-test, is because it's a better test. It's a more rigorous test. So that's why I don't want to confuse the issue now by throwing that monkey wrench into this whole thing. So I'll confuse it at the end of the semester. So you can leave with your head buzzing at the end of the semester instead. Okay, so I can reject the null hypothesis here, but it doesn't tell me which of these means are different. It doesn't tell me if the mean for the younger smokers is different from the mean for the middle-aged smokers, or the younger smokers are different from the oldest smokers, or the middle-aged smokers different from the oldest, or the middle-aged smokers are different from the youngest, and so on. In order to determine that, I need to run tests after I've determined I can reject the null hypothesis. If this came up to be bigger than 0.05, I failed to reject the null hypothesis. I'm done. I can't go on to post hoc tests. If this comes out to less than 0.05, well, now I can go on to post hoc tests. Okay, so I'm going to analyze this, compare means, one-way analysis of variance, right? Except now I'm going to go into post hoc tests, and I'm going to choose one of these post hoc tests. Most commonly, Bonferroni or Tukey, they're general purpose tests. They all have specific areas where they work best, but for our purpose, Bonferroni or Tukey will be suitable. So I'm going to use one of those two tests. I'm going to click continue, and I'm going to go ahead and run this analysis again. So it's going to do exactly the same analysis for our analysis of variance again, but now in addition to that, it's going to run a post hoc test. And in the post hoc test, it's going to compare each one of these three groups, group 1 to group 2, group 1 to group 3, group 2 to group 1, group 2 to group 3, group 3 to group 1, group 3 to group 2. Notice that each one of these happens twice. 1 to 2 happens here, but it also happens here, 1 to 2, 2 to 1. 1 to 2 and 2 to 1, same comparison, right? So it just does it for every possible permutation. So keep that in mind. So in order for me to reject any of these null hypothesis, mean for group 1 is equal to mean for age group 2, right? In order to reject them, the probability of being wrong if I reject them has to be less than 0.05. Well, this, I can't reject this. I can reject this. I can reject I can say that the mean for age range 1 is different than the mean from age range 2, with less than 5% chance of being wrong. Okay, so 1 to 3, the youngest versus the oldest, is different percentages of the population, of those populations that smoke. How about what are any others here? Well, this one, group 2 to group 3 is statistically different. And then finally at the end here, it just reiterates those first two. 3 to 1 is different, and 3 to 2 is different. Which ones are not different? Which ones did we not reject the null hypothesis for? 1 and 2, right? We weren't able to prove that 1 and 2 were different from one another. Okay, that's the point here. Not all of these means have to be different in order for you to get a significance that's small enough to reject the null hypothesis. So the null hypothesis might be mu is 1 is equal to mu 2 is equal to mu 3, but the alternative hypothesis is that at least two of the means are different. Not necessarily all of the means are different. Okay, so that's where we stand with analysis of variance. Okay, so are there any questions? So now this was a whirlwind review of 99% of the stuff we did from exam 1. You have many videos. In fact, I'm probably going to uh, pick and choose some of the videos and post them in an announcement on Blackboard, and highlight. Maybe put a little note on there. If you ask questions, I want to show you something quickly on Blackboard. On Blackboard, if you go into discussions, let me log on. And yes, my name is misspelled. There's two kinds of people. One kind of person that if he gets a stone in his shoe, he'll walk around for hours before he takes that stone out. There's another person can't walk 2 steps without getting so aggravated he takes the stone out immediately, right? This putting up for the last year and a half with my name being spelled wrong demonstrates that I'm the first kind of person, right? So I mean, a lot of other people would gone nuts every time they type their name in wrong. But at any rate, that's me. You guys may be different. Let's see, where was I here? Oh, I was going to go in here and show you that there is a specific location. I'm going to go into the discussions board. Okay, and in the discussions board, right at the top here, there was exam questions number 1, only 3 posts on that, right? And exam questions number 2. If you click into there, you can go in there and you can create a thread. You can create a thread and say, let's say t-test for proportions, right? How do I calculate standard error? Okay, or something like that, or margin of error, or something like that. Now, I'm not going to be so specific that I give away one of the answers on the exam, but I will give you as much help as I can on that. Or you might say question number 12. Question number 12, you might say, I think there's a typo. Shouldn't it say the what is the null hypothesis, not the hold hypothesis, or whatever, right? There might be some error on the test or something like that. I will be answering all those things. If there's, like typos or any errors or clarifications that you might need, I will be answering them here on Blackboard under the discussions forum. So you should check it every once in a while. If you have a question, post it to the discussions forum. You can create a thread yourself. You don't need me. Just go into that section, create a thread. I will check it every once in a while and I will keep it updated. Some of you guys use it pretty regularly. Most of you guys haven't taken advantage of it. But because I want to be fair to everyone, I will be anything that has anything to do with the test questions in relation to the test, I will be answering in that forum so that everybody sees the same information. Are there any embedded images in the? Yes, there are some embedded images. Oh, did you guys had some of you guys had a problem viewing the images, eh? Yeah, I'll go through it. Yeah, I'll go through it, and I will include as a JPEG somewhere else. Like just like I gave you. If there's a file you need, it's a separate place. You can open it from a separate place. I'll give you any JPEGs or images, PNG files or images that are on the exam that you might need to do some calculation. I'll let you know what question they're related to. I'm glad you brought that up because one or two people did have an issue with that. Okay. So I think so. Like I said, go to the discussions forum and take advantage of that so that we can all kind of share this. If you want, other students can share information. Do not give each other the answers to the questions. Do I have to tell you that? Probably not, right? Okay. But if somebody is trying to figure out, well, how do I do, what's the difference between where do I put stuff in the t-test? How do I, decide what to put into the values and what to put into uh, 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 what is it on the t-test? It's the uh, groups or the factors list, factors. What do I put into the factors? If you want to discuss that in general, I'm okay with that, but just not any specific questions. Okay, and if you have if there's a homework issue you have, there's also other places on there where you can ask me questions about the homework as well, or you can ask and give each other's help on the homework. Unlike that, I don't mind you guys actually working on the homework together on the forum, because that if you want to make that collaborative, you can, because if anything, I'd encourage you to work together as long as you all start eventually at the end wind up understanding how to do the homework, but limit it to maybe a question or two. Don't post the whole homework. Okay, so good luck on the exam. And on Wednesday, the exam's due on Thursday night at the end of the day. We're running out of time. I can't give you too much more time on this stuff because we still have a third exam, which will only cover two topics: correlation and what we did last week, chi-square and odds ratio. Wednesday, we're going to discuss correlation and regression. We're going to get into correlation and regression. We're going to continue with that on Monday. And the last exam I'll post over the weekend. The last exam I'll make due by the 25th, which is, by the 27th, which is maybe I can go to Saturday, 28th. Actual last day of classes presumably is the 25th, which is Wednesday, I think. And then we can go like a few days later before I have a little bit of leeway on grades, but not much. Trust me, not much. Get the work done. Most of these departments now are brutal where incompletes are concerned. You would have to go to your advisor to get okayed for an incomplete.